welcome back to the latest lecture session. So, we have obviously been looking at a relevant aspect or the case study relevant to soil vapor extraction, right. So, in that context we looked at a few details as in a particular site contaminated in Ohio, let us say, right, that is contaminated with PCE, TCE, 1,2-DCE, benzene and so on and so forth, and the contamination was both in the gaseous phase and in the aqueous phase, and this was used by corporations such as this, and the site was previously used by corporations such as Monsanto, and they dumped their waste there, and later on I believe a landfill was constructed, but obviously the relevant site was already contaminated, let us say, and a considerable what do we say section of the area was also, it seems, used for burning some of the waste. So, thus obviously you have relevant aspects. So, in this context gaseous and aqueous phase are contaminated, obviously soil also will be contaminated, right, these are hydrophobic compounds too, right. So, obviously people looked at soil vapor extraction, and to enhance it and get out the relevant contaminant from the water, they looked at air spurging, let us say, right. So, we were looking at those aspects, right, and let us look at the relevant details. So, obviously what do we have? We saw that they constructed both the air spurge well and the vapor extraction well in close proximity to each other. So, this is the ground surface, let us say, right, and here you have, let us say, the air spurging well where they are going to introduce air into the relevant system, right. They looks like they almost went till the bedrock here, right. We saw that there was some particular bedrock, and what do we have out here? Air diffuser. So, now you have bubbles of air, let us say, that are going to be released, let us say, right. So, you have these bubbles of uncontaminated air that are traveling through this particular contaminated groundwater. So, what is going to happen during this particular period, let us say, when you have the relevant air coming in, uncontaminated air coming in contact with this particular groundwater, you are obviously going to have, let us say, a change in phase of the contaminant from the aqueous phase into the gaseous phase, right, and here you have the relevant groundwater table as we can see here. So, that is what you see out here, and once as this particular gas or the bubbles leave the relevant groundwater, what is happening? You see that there is a net change in mass of the particular contaminant, right, from the aqueous phase or the water into the gaseous phase, right. So, anyway, we are just trying to promote or fasten the change in mass or transfer of mass from the aqueous phase into the gaseous phase. So, similarly at the same point or time, let us say, we are going to have relevant contaminated soil here in contact with contaminated groundwater. So, as the contaminant is removed from the groundwater, let us say, into the relevant gas, let us say, or the air bubble, let us say, right, you are also going to have desorption of the relevant contaminant from the soil into the groundwater, right. So, that is something to keep in mind. Again, they have cement grouting, bentonite seal, right, and so on and so forth. So, sand packs and so on, let us say. Again, the primary aspect is that they are going to bubble air through this particular groundwater table, and here you have the extraction well, let us say, right, and it is at relatively negative pressure, let us say, right, or vacuum source, depending upon where they have the vacuum source anyway. So, they are going to pump the gas out, right, and thus and then treat that further, I guess, right. This is what we have out here. So, extraction well contaminant concentration reduction percentage, obviously we are going to look at the amount of reduction that was noticed over this 3-year period. So, range from 35% to 100% and typically greater than 80%, let us say. So, I guess it would have been interesting if I was able to get more data regarding which particular contaminant, and we are going to look at that particular aspect out here, right. So, here we have different wells, right, different locations, right, and different what do we say compounds out here, right, and I believe this is the one in the gaseous phase if I am not wrong. So, typically let us say benzene, right, for some particular reason, let us say this particular well we have both 1,2-DCE and benzene removal to be slightly lesser than expected or desired, and typically let us say we see that dichloromethane, tetrachloroethylene and toluene, let us say, which are considerably volatile, considerable or 100% removal, and maybe not as much for 1,2-DCE and benzene, let us say. So, what are some of the aspects that can lead to such partial removals, let us say? If your contaminant is either present as the NaPl or present as benzene itself or as this 1,2-DCE itself, let us say, or you have an NaPl phase, or if you have considerable fractions adsorbed onto the relevant soil, let us say, right. So, the compound can also change phase from the water into the relevant what do we say, gas, right, or let us say if it is also very hydrophobic or it wants to be adsorbed onto the relevant soil too. In such a case, let us say even though you are going to have desorption from the soil, you know, you are depending on the kinetics or let us say the octanol water partitioning coefficient, let us say, you might not have complete removal, let us say, because here we are only trying to pump out the relevant air, right. So, but in general as you look at this particular data, let us say, you see that the removal percentage is pretty good, let us say. Again keep in mind that these are hydrophobic compounds and pump and treat or such mechanisms typically will not work out here, right. So, let us look at the total mass that was removed. So, two zones obviously, I think south and the west zones, right. So, we have different contaminants here. So, here in zone 1 relatively less, but in zone 2 you see a considerable amount, let us say, and what is this? This is in lb, let us say, or pounds, right. So, typically 2.2 pounds, let us say, is equal to 1 kg, let us say, right. So, now you get an idea about the total mass of these VOCs that were removed, let us say, right. So, that is something to keep in mind, right, more than a ton, let us say, ton of the relevant more than a ton, right, were removed out here, right. So, that is something to keep in mind. So, zone 1, let us say, right, let us look at that in greater detail. As I mentioned, they started pumping it out in 97 and to mid 2000, let us say, and here you have an idea about the time it was pumped for. So, looks like almost 1300 hours, let us say, right. So, again for different what do we say, contaminants, keep in mind this is ppm volume. So, this is in the gaseous phase, right. All these concentrations are the concentrations in the gaseous phase. So, benzene we started out with 0.58, end up with 0.002. This is obviously a particular well, let us say. So, thus 12 DCA at 33 and again 0.045 and again 0.25, 0.012 and 8.3 toluene we start at relatively higher concentrations and at relatively low concentrations. Trichloroethene, let us say, again 0.105, again not as much removal as you would expect, but could be due to the compound being relatively more hydrophobic onto the relevant soil and such, but again that is some data that you can look up, let us say. But try to look at the relevant aspects, let us say. Initially, let us say when the concentration is high, let us say, right, what is going to happen, let us say, if you introduce fresh air or uncontaminated air in contact with contaminated groundwater, let us say, then you know more of the contaminant will be released, let us say. But over time what is going to happen, the concentration in the relevant gas or the relevant water, let us say, will come down, let us say, right, or will be decreased. But it is not decreased to such a level, let us say, that it is safe enough, let us say, or you know has met the standards. But because the concentration is relatively low, right, you will now need to have a lot of pump a lot of gas to be able to remove this what we say relatively little mass of the contaminant, right. So, again why is that? The gradient, let us say, or the difference in concentration, let us say, between the uncontaminated gas and the relevant water or the uncontaminated gas and the relevant soil, let us say, is relatively less, let us say, right. So, again we know that it is a equilibrium, right, there is always going to be an equilibrium. So, the lesser it is, let us say, right, you need to obviously have more and more volumes of air that need to be pumped out obviously. Let us say if you look at, let us say, per time or over how much time, let us say, a percentage of removal, let us say, right. So, you will see that initially, let us say, a great percentage of removal would have occurred and later on, let us say, over a considerable fraction of time, let us say, or period of time, pardon me, relatively less what do we say, fraction of the relevant or percentage of the relevant compound would have been reduced, right. So, let us try to look at those aspects here. So, here we have one particular graph here, and what do we have here? So, this is the concentration on the y axis in ppm volume units, right, volume by volume, right, and here time from 0 to around 1300 hours as we saw in the previous table, right. So, 1300 hours as we see out here, and different compounds out here. As we looked at it, toluene relatively higher concentration initially, and then also 1,2 DCE, let us say, relatively high concentration initially, right. Others may be not so high, but again what were we talking about earlier? As you see, right, here we started out with I think 40 or so, let us say, and within let us say 300 or 350 hours, right, we are almost at more than or almost at 90% or 80% removal, let us say. We are able to capture 80% of the mass within 350 hours, let us say, right. But as you can see, you still have considerable mass and rebounds out here. This is a rebound, maybe they stopped the pumping out here, and then you have desorption from the soil, and the contaminant concentration increasing, and then again pumping out and so on and so forth. You see that they had to keep pumping the relevant contaminant for or running the system for a considerable amount of time. The same case with what is it now 1,2-DCE2, right. So, that is what you see here. So, we are starting around 32 or something, and within maybe 175 or 180 hours we are almost achieving 80% removal, but let us say again you need to keep pumping it because the lower you go, let us say, right, again keep in mind because of the effects of equilibrium, let us say, right, you are still going to have to pump a lot of volume of air, right. So, that is something that you see out here, right. So, let us move on. So, zone 2, right. I believe we were able to or we saw that there was greater contamination in zone 2, right, as in zone 1 around only 150 pounds, and zone 2 almost 3,300 pounds, right. So, that is something to keep in mind. So, let us look at the zone 2 data. So, similar picture probably, but we start out with much higher concentrations for almost all the relevant compounds, let us say. Again toluene, as you see, it is 220 out here, TCE is 130 out here, and so on. We started 97 and so on. So, 28 hours here they obviously had to run it for more time, let us say. And why is that? Obviously, you have more what do we say mass out there, thus you need to pump more volume of air through, let us say, right, to be able to remove that particular contaminant, and thus the time required is obviously going to be relatively higher, let us say, right. So, let us look at the relevant aspects again, 2.3 to 0.009, 130 to 0.874, 1.6 to 0.054. As you can see, let us say some of the compounds, right, the percentage of removal is relatively less. So, 10 to 0.1, right, 220 to 1.1 still relatively high, 130 to 7.6, and here you see rebound here, right. I think he rebound in this particular cases, maybe they stop pumping out here, right. So, you see some rebound out here, right. So, that is something to keep in mind. What is this rebound now? So, I am pumping out the relevant air, and then I stop pumping the relevant what do we say air, let us say. What is going to happen now? So, equilibrium is going to be reached, let us see. As when I say equilibrium is going to be reached, what is going to happen? The contaminant can dissolve from the relevant soil into the water, and then there is again going to be an equilibrium between the water and the gaseous phase, right. So, now the concentration is going to increase, let us say. So, that is what you see out here in this particular period typically, right. So, let us look at the other set of data too, and they continued it till again May 2000, right. So, they ran it for a total of almost 17,000 hours, right. So, that is something to keep in mind, right, and then achieved, I guess, the relevant standards and so on. Again, as you see, the mass removed, let us say, is going to be decreasing. Mass removed per mass of air or volume of air that you pumped out will keep decreasing with time. Why is that? Because right now, not right now, let us say in the later stages I do not have as much contaminant. So, when I let the system equilibrate, let us say only small amount of contaminant will be removed in the gaseous phase, right. So, that is what we see out here. Let us look at the graphs too, right. So, again as you can see, we start out with what is this now for tetrachloroethene, let us say PCE, right, somewhere around here in 10. Again almost 90% removal within maybe 1000 hours, let us say, but we still had to keep pumping it out, let us say, to remove those or the relevant trace concentrations, right. That is something that we see out here, but I guess the picture is not greatly clear. We are going to break that down, right. So, the same picture, let us say, from 0 to 2500, as we mentioned earlier, within 1000 hours, let us say, right, we were able to capture almost 90% of the relevant contaminant, let us say, right. And same case with, let us say, you see that with benzene and dichloromethane, let us say, right. So, relatively similar profiles. So, the next fraction, let us say, as you can see here, you can see the effects of rebound, let us say, here you see increase here from time to time. So, that means that they have not obviously pumped the system out or gas out continuously, right. They let the system rebound, right. As in, let us say there is this mass of contaminant in the gaseous phase, I remove this, and then if I keep pumping it, what is going to happen? I am only going to keep pump out relatively less contaminated air. So, the efficiency of my system is relatively less. So, what would I do? I will stop pumping for some time and then let the system reach equilibrium between the soil, gas and the aqueous phase, or at least try to have more contaminant now in the gaseous phase, and then I will pump out that particular contaminated gas. So, that is why you see these particular rebounds, and I guess they stopped pumping, or there was some particular reason why there was considerable rebound out here, right. And you see though, right, you need to pump for considerable amount of time for a net removal, let us say, at when you have concentrations at relatively low levels, right. So that is something that we have out here. Again, this is the bigger picture. We looked at this particular case, I believe, until now, and then looked at this particular case. But as we looked at it in this particular set of data, we saw that they let the system rebound and then pumped the relevant contaminant out, right. So that is something to keep in mind. So for the other sets of contaminants, if you remember, toluene was at relatively high concentrations, 220 or something, that is what we see out here. Again, same picture, let us say almost 90 to 80% within a fraction of the time, let us say, or fraction of the total volume of air. And for relatively less removal, let us say less than 10%, again you had to pump for considerable amount of time, let us say, right. So again, this is from 2500 to 18,000. Again, what do we see here? We see that the relevant people let the system rebound or equilibrate, they stopped pumping. So the system equilibrates, then they kept pumping, again they pump it up again. Let me try to change the color here. So here you see that there is a decrease and then increase. Why is that? That typically means they stopped pumping at this particular case and then again kept pumping. So they decreased, it as in concentration of the contaminant in the gaseous phase decreased and then again stopped pumping. So again you see an increase, again kept pumping, right. So it goes in phases, but you see that typically the maximums will keep decreasing over time, let us say, right. So that is what you see out here, right. So that is something to keep in mind. So obviously, we need to understand the relevant aspects as in the relevant costs and such, let us say what are the relevant factors or variables that add to the relevant cost, let us see. But typically what do we need, as you know, where do you need to spend considerable amount of money? Certainly, let us say when you are looking at monitoring the relevant locations and estimating the relevant concentrations of the contaminants initially, that is one particular aspect, right, or even monitoring the relevant locations with time. So that is the major aspect out here, or a considerable aspect. Obviously your air spudging and extraction system, let us say, is also going to take up considerable amount of money and resources, and certainly let us say you need to put in a lot of or considerable fraction of the resources into extraction, let us say, right, as in not extraction, pardon me, into your relevant what is it now, site characterization, right. So let us look at these aspects. So they removed almost 3,400 pounds, let us say, right, more than a ton, let us say, or 1.5 ton, I guess, right, or 1.25 tons of soil vapor contaminant. That is a considerable mass, and they, I believe, they ran the system for 2.5 years, right, and again it was not continuous operation. So from time to time, let us say. So total project cost was around, I believe, what is this now, 14 million, is it? No, it is 1 million, right, or 14,39,000 dollars, or 1.4 million dollars, let us say, right. And keeping in mind the type of contaminant that we have, right, which is VOCs, let us say, which are VOCs, right, this project cost is very much reasonable, right. Typically maybe we looked at some of the other examples, let us say, and you might have seen cases where they went into tens of millions of dollars. Obviously here we looked at relatively smaller area, let us say, I think LB area or soil area or such, and only a fraction of a 306 acre site, right. But again, keep in mind that they pumped out considerable mass of the contaminant, let us say, and for around 1.4 million dollars, let us say, right. So cost per pound turn out to be $365, let us say, that is typically reasonable. Let us look at the breakdown now, right. So initially, let us say, again, cost element, description, cost and subtotal, let us say, right. So we are going to look at, let us say, the initial phases, mobilization and preparatory work, right. So site preparation, considerable what do we say amount, let us say, and demobilization and site restoration, let us say. So that is a fraction of the relevant aspects. So as we mentioned earlier, monitoring, sampling, testing and analysis will take considerable or will require considerable resources. So let us look at that. So sampling performance monitoring, right, sampling compliance monitoring. So as you see, typically let us say you are not going to just spend money, let us say, on trying to get data. You will also spend considerable data, as you will see in out here, and especially in compliance monitoring, let us say, also let us say, to be able to understand, let us say, the quality, let us say, required to maintain that particular data, as in sampling, quality assurance and quality control, analysis, quality assurance and quality control, and so on and such, right. And why is that? Obviously you need to have confidence in the data that you are generating, right? If the data that you are generating, let's say, is erroneous due to, let's say, different aspects, analytical error, human error, or so on and so forth, let's say, or if errors crept in over time, let's say, right, your system is going to, you know, seem as if it failed, but it's that your underlying data, let's say, or assumptions were erroneous, right? So obviously, to look at those aspects, you obviously need to look at, you know, the quality assurance and quality control, which is a very important aspect, let's say. And here again for them, let's say, sampling compliance monitoring, let's say, right, even for sampling compliance as in to meet the relevant regulations, I guess, during monitoring, let's say, and sampling, let's say, you know, looks like they had to pay considerable amount of money. Analysis compliance monitoring, again, right, geoprobe sampling, maybe not a cost. On-site automated GC, GC is a gas chromatograph, so looks like that cost, you know, they, rather than taking it off-site, it as in the contaminant somewhere else and analyzing it, so that might add up to a considerable fraction of money. They place the analytical equipment on site itself, and that is a gas chromatograph, let us say, right. And sampling and analysis supplies, right. So more or less almost 10% of the project cost is within, or you know, is due to monitoring, sampling, testing, and relevant analysis, let us say, right. So groundwater collection and control and so on and so forth, right. You know, we have the relevant data out here, right, and that is, I guess, for groundwater maybe not as much, let us say, right. So that is something out here, $55,000. Obviously air sponging and soil vapor extraction will take up considerable, what do we say, amounts, let us say, and let us see what we have. So above ground equipment purchase, below ground and above ground installation. Below ground installation costs are obviously considerably high, let us say, right. Obviously contract operating costs, but obviously below ground installation costs, and you see that this is almost, let us say, 15 to 20% of the total cost, let us say, right. And then soil vapor extraction, let us say, let us look at the major aspects here. Again, above and below the ground installation, right, is quite costly compared to the actual purchase of the relevant equipment. And again, keep in mind that if you do not get the locations right or the placements right, let us say, right, you are going to be able to, you know, or mess up the relevant system. So as you see, a considerable fraction of the money is spent on installation, let us say, right, rather than the actual capital cost, right. Again, 10% or 15% of your relevant cost, let us see. And then again, project management and engineering general requirements, that obviously took up, what do we see, I guess we do not have a great deal of background here, not background, pardon me, data here, but again it is for operation and maintenance. As you see, they ran it for thousands of hours, I think 2,500 hours in one particular zone, and then greater than 10,000 hours in, or around 10,000 hours in another particular zone. So obviously you are going to have relevant bills to pay, right, both the utility bills for the labor and so on and so forth. So I guess these are the relevant aspects, and that they end up almost around 70%, let us say, of the relevant cost, let us say, right. So I guess with that I am going to end my particular what we say case study for soil vapor extraction. But again, the key aspect is that, let us say, right, we need to obviously look at, let us say, relatively permeable soil, or the relevant site needs to be relatively permeable, right. And even though the contamination has taken over a long period of time, let us say, you are still going to have concentrations present, as in considerable concentrations in the relevant soil. Why is it? Because they are remarkably hydrophobic, let us say, right, and some of them are very toxic to the microbes, as in the site was used from 1947 to 1997, and even in 1997, let us say 50 years down the line, they still observe very high concentrations of the relevant contaminants, let us say, right. So I guess with that I am going to end today's session, and thank you.